Assalamu alaikum, dear students. In today's lecture, we are going to start chapter number 1 of the textbook. And in this lecture, we will discuss propositional logic, which is the section 1.1 of chapter 1. So this is the first section of chapter 1. So let's have a look at the summary of the chapter. And chapter title is Foundations, Logic and Proofs. So in this chapter, we are going to study propositional logic, predicate logic, proofs, rules of inference, proof methods, proof strategies, the language of proposition, and some applications, logical equivalences. So section 1.1, which is about propositional logic. Now it consists of two terms, propositional logic. So let's see what is proposition and what is propositional logic. So let's reveal in later slides. So section summary, in this section we'll be defining proposition, and we'll learn few connectives like negation, conjunction, disjunction, implication, contrapositive, inverse, converse, and biconditional. And we'll learn how to make truth tables for all these conjunctions, all these connectives. So first of all, proposition, definition of proposition. What is proposition? A proposition is a declarative sentence that is either true or false. A proposition is declarative sentence. So it is a sentence which declares some fact which can either be true or false. There is nothing, no other option. So there are few examples of proposition, like the moon is made of green cheese. Lahore is capital of Pakistan. So all these are declarative sentences which can either be true or false. Toronto is capital of Canada. 1 plus 1 is equal to 2. 0 plus 1 is equal to 2. Now 0 plus 1 is equal to 2 is false. 1 plus 1 is equal to 2 is true. Toronto is capital of Canada. This is true. So you can see in this example, we can declare every statement either true or false. Now there are examples which are not propositions. That is, we cannot declare for the statements that they are either true or false. Let's see. First statement is sit down. This is not actually a statement. This can be a request. Someone is requesting you to sit down, or someone is ordering you to sit down. So this is not declaring some fact. So this is not a proposition. What time is it? This is a question. So this is also not a proposition. X plus 1 is equal to 2. So since x is variable, so we have to assign some values in order to make it true, or for other values this statement will be false. So this is not either, this cannot be declared either true or false. This is true for some values of x and this is false for some values of x. So this is not a proposition. X plus y is equal to z. Again, it involves variables. So this is again not a proposition by the definition of the proposition just we stated. Now, what is propositional logic? The area of logic that deals with propositions is called the propositional calculus or propositional logic. So constructing propositions, we need variables. So we have to assign variables to the statement which is a proposition. For example, if I say that my name is Misbah, so in order to use this statement later on, I have to assign a variable to this statement. Similarly, if I live in Lahore, then I have to assign some variable to this statement in order to use in further applications. The proposition that is always true is denoted by T, or in bits it is denoted by 1. And the proposition that is always false denoted by F, or in bits it is denoted by 0. Compound propositions are the propositions which are constructed from logical connectives and other propositions. So what are the logical connectives? There is first connective which is called negation, and this is the one which we can apply on only one proposition. Conjunction, for this we need at least two propositions to apply on. Disjunction, and there are symbols given for all these propositions. You can see this is symbol of negation, this is symbol of conjunction, this is symbol of disjunction. Implication, this arrow is the symbol of implication. Biconditionals, this double-sided arrow is the symbol of biconditional. Compound propositions, first of all, let's see what is negation. The negation of a proposition P is denoted by negation P. We read it as negation P or not P. And is the statement, it is not the case that P. That is, if P is the statement, my name is Misbah, then negation P will be, this is not the case, my name is Misbah, or my name is not Misbah. So truth value, let's form a truth table for negation P. So truth table for negation P will look like this. We have only one proposition. In order to make table, we only need two rows because P can either be true or false. So whenever P is true, negation P is false. Negation P has opposite truth value. So if P is false, then negation P is true. So there is an example. The earth is round. If P is the statement that the earth is round, and then negation P denotes it is not the case that earth is round. Or more simply, we can say that the earth is not round. Conjunction. And the symbol for conjunction looks like this, hat-like symbol. The conjunction of proposition P and Q is denoted by P and Q. This is read by P and Q. So the conjunction P and Q is true when both P and Q are true. So this is very important to note. It will help us making a truth table for this conjunction, and is false otherwise, right? So this is true only when P and Q both are true, otherwise it is false. So let's make the truth table for this conjunction operator. So in this case, you can see that in this connective, we have two propositions, at least two propositions. So P and Q. Now, how many possibilities are there for P and Q? So if P is true, Q can be true. P is true, Q can be false. If P is false, then Q can be true and false both. So we have 4 rows to make this table. So we have 2 variables and we have 4 rows. In previous slide for negation, we had 1 variable and we had 2 rows. So just keep this pattern in mind. We'll generalize this at the end of the session. So P and Q, according to the definition, this column indicates the truth values for P and Q. Now if P is true, Q is true, P and Q is true. According to the definition, P and Q is true when both P and Q are true. Otherwise it is false. So when P is true, Q is false, this is false. P is true, Q is P is false, Q is true, this is false. P is false, Q is false. That is, both are false. Then P and Q is also false. Now if P denotes I am at home and Q denotes it is raining. So P and Q will be the sentence I am at home and it is raining. Simple. Disjunction, and the symbol for disjunction looks like this. So disjunction of propositions P and Q denoted by P or Q. This is called OR operator. P or Q is the proposition P or Q, and the disjunction P or Q is false when both P and Q are false. Otherwise, it is true. So let's have a look at its truth table. So again, we are using two variables, propositional variables, in this truth table. So we have 4 rows in the table. So this column represents the truth values, corresponding truth values for P or Q. Now, according to the definition, when P, Q both are true, P or Q is true. If one of P and Q is true, then P is true, true. If both P and Q are false, then P or Q is false. So if P denotes I am at home and Q denotes it is raining, then P or Q denotes I am at home or it is raining. So in English, or has 2 distinct meanings. So one of the meaning we have already discussed, this is called inclusive or, and there is another type of or which is called exclusive or. So in case of exclusive or of 2 propositions P and Q, this is denoted by this symbol. One of P and Q must be true, but not both. So P exclusive or Q will be true if one of the P and Q is true. Otherwise, it is false. That is, if P and Q both are true, it is false. If P and Q both are false, it is again false. So its truth table will look like this. So you can see that this is true only when one of P or Q is true. So this is false when both are true. This is false when both are false. So this is called exclusive or. So there is an example to have deep understanding of this exclusive or. When you buy a new car from Acme Motor Company, you can get $2,000 back in cash or 2% car loan. So you cannot get both at a time. So either you will get $2,000 cash back or you will get 2% car loan. So at the same time, both cannot happen. So that is why when we will use propositions variable for this, a proposition connectives for this statement. So for this statement, we'll use exclusive or. Implication, and symbol for implication looks like this arrow. If P and Q are the propositions, then P implies Q is a conditional statement. This is also called conditional statement or implication, which is read as if P, then Q. So P implies Q means if P, then Q, and has this truth table. So this is false only when P is true and Q is false. Otherwise, it is true. This is false only when P is true, Q is false. Otherwise, this conditional statement is true. So if P denotes I am at home and Q denotes it is raining, then P implies Q denotes if I am at home, then it is raining. As we say, okay, P implies Q means if P, then Q, right? So P implies Q in this case denotes if I am at home, because P denotes I am at home. If I am at home, then it is raining. In P implies Q, P is called hypothesis, premise, antecedent, and Q is called the conclusion or the consequence. Now, understanding implications, in P implies Q, there does not need to be any connection between the antecedent or the consequent or the consequence. The meaning of P implies Q depends only on truth values of P and Q. And in last table we said that, in last definition we said that this is false only when P is true and Q is false. You can see that P is true, Q is false. Otherwise, it is true. So this depends upon the truth value of P and Q. These implications are perfectly fine, but would not be used in ordinary English, like if the moon is made of cream cheese, then I have more money than Bill Gates. We don't use these sentences in daily life because such sentences do not make sense in English. But in logic, we can use this, and these are conditional statements. If the moon is made of cream cheese, then I am on welfare. If 1 plus 1 is 3, then your grandma wears combat boots. One way to view the logical conditional is to think of an obligation or contract, like if I am elected, then I lower taxes. If you get 100% on finals, then you will get an A. So if politician is selected and does not lower taxes, then the voters can say that he or she has broken the campaign pledge. So something similar holds for the professor. This corresponds to the case where P is true and Q is false. P is true and Q is false. So in this case, P implies Q is false. So there are different ways, several ways to express P implies Q. So they are listed, few of them. If P, then Q. If P, Q. P implies Q. P only if Q. Q unless negation P. All these are equivalent to P implies Q. So keep this in mind. Q when P. Q if P. Q whenever P. Or P is sufficient for Q. P implies P, Q means P is sufficient for Q, or Q is necessary for P. P implies Q also indicates Q is necessary for P. A necessary condition for P is Q. Actually, these two are derived from these two. And a sufficient condition for Q is P. So what is the value? There is an example. What is the value of x after the statement, if 2 plus 2 is equal to 4, then x is equal to x plus 1. If x is equal to 0, before this statement is encountered in a program. So the symbol stands for assignment, that we are assigning the value to the variable. And the statement x is equal to x plus 1 means the assignment of value of x plus 1 to x, right? So initially x is equal to 0. So keeping this in mind, x is equal to 0. Now since 2 plus 2 is 4, and this is true, 2 plus 2, 4 is true, the assignment statement will be executed. So after execution, what will be the value of x? X is x plus 1. What is the initial value of x? This is 0. So next new value of x will be 0 plus 1 equal to 1 after this statement is encountered. Now there are few terms related to conditional statement: converse, contrapositive, and inverse. So from P implies Q, we can form new conditional statements. Q implies P, and this is called converse of P implies Q. Negation Q implies negation P. This is contrapositive of P implies Q. Negation P, that is, we are not going to change order in this case. And in both the cases, you can see order of this conditional has been changed. So we are not going to change the order, but we are just going to take negation of both the propositions used in this conditional statement. So negation P implies negation Q. This is called the inverse of P implies Q. So find the converse, inverse, and contrapositive of it raining is a sufficient condition for my not going to town. So raining is actually, you can read it as raining is sufficient condition for my not going to town. So you can assign variables It is raining, P, and I'm not going to town is Q, for example, right? So P is sufficient condition for Q, right? P is sufficient condition for Q. P is sufficient for Q. What does this mean? P implies Q, right? Now you have to write converse, inverse, and contrapositive. So what will be the converse of this statement? Converse is Q implies P. So converse is, if I do not go to town, then it is raining. We are just going to reverse the process. That is, this is P implies Q. So converse will be Q implies P, right? If I do not go to town, then it is raining. Inverse. Inverse is negation P implies negation Q. If it is not raining, then I'll go to town. So we have negated both P and Q. P is, it is raining. This statement means, P implies Q means, if it is raining, then I'm not going to town. Right? You can rephrase this like, if it is raining, I'm not going to town. So its converse is, if I do not go to town, then it is raining. We just have reversed the order. P implies Q. So this is the statement Q implies P. Now in inverse, what we are going to do, we are negating both P and Q. So if it is not raining, then I'll go to town. So what about contrapositive? Contrapositive is negation Q, negation P. So what is the negation Q? If I go to town, right? If I go to town, then it is not raining. So these are the converse, inverse, and contrapositive of this statement. Now there is an other connective which is called biconditional. If P and Q are propositions, then we can form the biconditional proposition P if and only if Q. This is read as P if and only if Q. And the symbol for this biconditional is double-edged arrow. The biconditional P if and only if Q denotes the proposition with this truth table. So you can see that if both are true, this is true. If both are false, this is false. This is also equivalent to P implies Q and Q implies P. So you should verify it yourself by making a truth table. So if we denote P, I am at home, and Q is denoted by it is raining, then P implies Q denotes I am at home if and only if it is raining, right? So this is the biconditional of P and Q. So some alternative ways for P if and only if Q are: P is necessary and sufficient for Q. If P, then Q, and conversely, P if and only if Q. So note that P if and only if Q has exactly the same truth value. P implies Q and Q implies P. I just told you in previous slide, and you have to verify it yourself. So P if and only if Q has exactly same truth value as P implies Q and Q implies P. Well, there is another example. Let P be the statement, you can take the flight, and Q be the statement, you buy a ticket. Then P if and only if is the statement, you can take the flight if and only if you buy a ticket. So here is the truth table. So this statement is true if P and Q are either both true or both false. So biconditional is true if and only if both P and Q are either true or false. That is, if you buy a ticket, can take the flight, or if you do not buy a ticket and you cannot take the flight, it is false when P and Q have opposite truth values. So in simple words, you can say that if P and Q have opposite truth values, then P if and only if Q is false. Truth tables for compound propositions. So construction of truth tables, we need rows. Need a row for every possible combination of values of the atomic propositions, whatever the propositions we are going to use in the statement. We have to assign one row for one combination. Columns, we need columns for the compound propositions. Need a column for the truth value of each expression that occurs in the compound proposition as it is built up. So, for example, if we have to form the truth table for P or Q implies negation R. So, what we need to do, we have to assign one column for P, one column for Q, one column for R, because this statement consists of 3 variables. Now, for 3 variables, how many rows are required? 8. 1, 2, 3, 4, 5, 6, 7, 8. All true, 2 true, 1 false, then 2 false, 1 true, and then all false. So you can verify it yourself. If you have 3 variables, you need 8 rows. If you had 2 variables, only 4 rows were required. If we had 1 variable, only 2 rows were required. So now negation R is used in this statement, so we have to assign a column for negation R. Then P or Q is used in this statement, so we have to assign a column for the truth values of P or Q. And finally, P or Q implies negation R. We will use conditional on these 2 columns. P or Q implies negation R. Right? So this is how we can form a truth table for the compound statement. Equivalent propositions. True propositions are equivalent if they always have the same truth value. For example, show using a truth table by using a truth table that the conditional is equivalent to the contrapositive. So conditional is P implies Q, and contrapositive is negation P implies negation. Negation Q implies negation P. This is the contrapositive. So again, we have to assign one column for P, truth values of P, one column for truth values of Q, and since negation P and negation Q are involved, so one column is dedicated to negation truth values of negation P and negation Q, and then we need P implies Q because we have to show both conditional and contrapositive, and the last column is for contrapositive. Using a truth table to show non-equivalence. So show using truth tables that neither the converse nor inverse of an implication are not equivalent to the implication. So again, we made this truth table in order to show that that all these are not equal. You can see in first row these are equal, but this row makes the difference. Right? So these conditional, converse, and inverse all are not equal. So problem here is how many rows are there in a truth table. So finally we have the problem I used to discuss in previous slides. How many rows are there in a truth table with n propositional variables? So the answer is 2 to the power n. Right? When there was only one variable, we had 2 rows, that is 2 to the power 1. When we had two variables, we had 4 rows. When we had 3 variables, we had 8 rows. So If we have n variables, then we must have 2 to the power n rows to construct the truth table. So note that this means that with n propositional variable, we can construct 2 to the power n distinct propositions. So that's all for today.